So uncertainties is a very simple one to start with. Any physical measurement is liable to uncertainty. I.e., we can't just take a reading and be 100% sure that that will definitely be correct. And that's got to do with different types of uncertainties I'm going to talk about. So the first type of uncertainty we're going to talk about is random uncertainties. Are fluctuations in a measured value due to small changes out with our control. So for example, if you let a trolley roll down a slope and you're using light gate, so you've made it as accurate as you possibly can, but if you just keep repeating that, you won't always get the exact same time, because there can be slight changes in, say, the background temperature, which very slightly alter the amount of air resistance, so you get tiny fluctuations that you can't do anything about. Systematic uncertainties and incidentally, you often hear the word errors used instead of uncertainties. I think that confuses people a wee bit. It's not necessarily that you're doing anything wrong. That's why I think the word uncertainties is a bit clearer. So systematic uncertainties are due to faulty equipment or incorrect use of equipment. So for example, if the end of your meter stick had worn away and you were butting that up against something to take a measurement, then all your readings would be out. Or, more obvious one probably, if you use a set of scales but they don't read zero before you use them, if they're not zeroed, then all your readings will be out. But that's not the fault of the equipment, that's you not using it correctly. And the last one we call reading uncertainties. And they are an indication of the precision of a piece of apparatus. So for example, a meter stick, right, has millimetre grades on it, whereas a tape measure might have 1 centimetre grades on it. So you can use them both for measuring lengths, but we'll see that they've got different reading uncertainties associated with them. So for repeated measurements of a quantity are desirable because they identify that random uncertainties are present. So if I go back to that idea of you're rolling something down a ramp, if you only take one measurement, you don't actually know that random uncertainties are present. So when you do it more than once, that becomes clear. And when we repeat measurements, the mean is taken as the best estimate, i.e. what we think our actual answer is. So the mean of a set of repeated measurements and this should actually really be written as 5 and 6 together. I don't know why the learning outcomes put the example before the definition. Calculate the mean value for a trolley to roll down a slope at the individual times and the mean value, so our answer here, it's the total of all values divided by the number of values. So in this example that would be 1.03 all divided by 4, giving a final answer of 1.05 seconds. So when a systematic uncertainty is present, all readings will be affected in the same way. So unlike the random variations where you can get some high, some low, all of them would be high, all of them would be low. So for instance, if we go back to a set of scales, if before you stood on them it read 2 kilograms, all your readings would be 2 kilograms too high. And repeating those measurements wouldn't actually reveal that. So repeated measurements are only important for revealing random uncertainties. Systematic, you've got to kind of work out for yourself, or as we'll see later, they can become apparent when you look at graphs of data. So now what we want to do is to try and put numbers to these uncertainties with the idea that once you can quantify them, you can then talk about comparing them. You can get a feel for how big or how small they are. So first of all, for random uncertainties, we've got a formula. So the approximate value for a random uncertainty, and this is just an estimate, it's a way of producing results that you can then compare. And the definition is the range of values, i.e. the biggest value take away the smallest value, divided by the number of readings. And what this formula really is saying is, if your range is really small, i.e. when you repeat your measurements they're all quite close together, then that's good. You're going to get a small uncertainty, you're going to feel more sure, less uncertain about your reading. And similarly, if you keep repeating readings, then that's going to make this uncertainty smaller as well. So if you get a range of readings from 4, and then you make 40 measurements, and you've still got that same range, well, that would make you feel more certain about it. So that would reduce the uncertainty because the number of readings would go up. Okay, and that would be most obvious when we'll look at an example of that. So if we return to the data that we used in example 5 and 6, then the range of readings, the largest one there was 1.07, the smallest was 1.03, there were 4 readings, So the random uncertainty in that particular set of readings would be 0.01 seconds. Now, basically, systematic uncertainty should be eliminated, so we don't really have a formula for them. And for reading uncertainties, we have a rule. For analog equipment, okay, so things like rulers or old style dials which have pointers, the reading uncertainty is half the smallest division. So if we go back to the example of a meter stick, if the smallest division in the meter stick is 1 millimetre, then you can read that to the nearest half millimetre, i.e. you can judge is it exactly lined up with one of those millimetre marks, or is it in the middle between them. When you use digital equipment though, which simply give you a readout on a screen, then you have no way of knowing if the reading is halfway between a particular value and the next one. So it's 1 unit of the smallest digit. So if you go back to those timings that we were looking at earlier, so those timings were given as 1.03, 1.05, etc. So the reading uncertainty for each of them would have been 0.01, which happens in this particular example to be the same as a random uncertainty, but that won't always be the case. It's often useful to express an uncertainty as a percentage rather than just its actual value. So for instance, if you're trying to measure the width of a classroom, 12 metres across, say, then an uncertainty of 1 centimetre in that is not really that significant. But if you're trying to measure the width of a human hair, then an uncertainty of 1 centimetre is huge. So to get an idea of the kind of relative size of uncertainties, we often express them in percentage form. So it's just the basic idea you'd have that a percentage uncertainty, so use P, is what we call the absolute uncertainty. So that's just the actual value of the uncertainty. So the 1 centimetre in the example I was talking about a wee second ago, divided by the value of the reading times 100%. Okay, so for example, if that was the one I just gave, if that was 0.01, so 1 centimetre, right, changed into metres, divided by 12 metres times 100%, which would be 0.083 recurring, but we usually only give uncertainties to one significant figure, so we'll just round that to 8%, or 0.08%, which is an incredibly small uncertainty in the example I gave there, but you get the idea hopefully. Now number 11 then is really just going to come from looking at examples, and it's just that idea that you work out percentage uncertainties from a few different quantities and then pick the largest. But the kind of key idea that we're going to put with that is that that largest percentage uncertainty in the measurements that contribute to value, so I'll do a worked example in a wee second. So for instance, if you're trying to work out a resistance and you measure a voltage and a current, so the largest percentage uncertainty in the measurements that contribute to a value is taken, and this is a very simple rule. Okay, you would meet more complex rules as you continue on, but it's taken to be the percentage uncertainty in the value. It sounds complicated, but it's actually really simple. So e.g., if you had taken a measurement of voltage, which was 3.2 plus or minus 0.1 volt, and you had a measurement of current, which was 10.0, oops, I'm not putting the units in yet, plus or minus 0.1 milliamp. Now we can see both these uncertainties are both 0.1, but then what we want to do is to get an idea of the relative value by working them out as percentages, and then we simply pick the largest of them to be the uncertainty in our final answer. So we can go ahead and calculate the resistance equals V divided by I, and for that our milliamps needs to be converted to amps. Okay, but now what we're going to do for each is for the voltage, the percentage uncertainty, unfortunately we don't have nice symbols for these, is 0.1, the uncertainty for the voltage divided by the value times 100%, and the same for the current is 0.1 divided by 10.0 times 100%. I'll work out both of them. And just in the middle of calculation, we'll worry about rounding off to one significant figure at the end. We'll leave that 3.1%, and that actually comes out to be exactly 1%. So the largest uncertainty comes from the measurement of the voltage in this case. But then we simply take that as the uncertainty in the final answer. So what we're saying is that our resistance is 320 ohms plus or minus 3.1%. So that would actually be an acceptable answer. But quite often the question will ask you to work out the resistance with its absolute uncertainty. So what we'll need to do is 3.1% of 320 to turn it back into an actual value, a resistance in this case. So we can do our calculation. And remember, percent means divided by 100. Is 9.92, which will round off to 10 ohms, because we want one significant figure. So our final answer for resistance then would be 320 plus or minus 10 ohms. I just realised that covers learning outcome 13 as well.